The morning of January 5, 1943, the North Atlantic lay frozen beneath a pale horizon. A convoy bound for Murmansk pushed eastward through black water streaked with ice. Near the center steamed a Liberty ship named the SS Schenectady, its hull trembling under the strain of subzero temperature and heavy sea. Just after midnight, as the ship lay docked at Swan Island Shipyard in Portland, Oregon, safe, not even under attack, the unthinkable happened. Without warning, a thunderous crack split the night. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The ship broke cleanly in two. The sound was like cannon fire. Steel plates tore apart in slow motion, twisting and curling upward as the midsection rose out of the water. The bow and stern sagged in opposite directions. Witnesses recalled a deep groaning sound, followed by a deafening snap as the deck plates ripped open. Men rushed from nearby workshops, expecting a boiler explosion. Instead, they found the Schenectady nearly folded in half at the pier. Its keel snapped clean through, as if sliced by a giant blade. It was not the first ship to break apart, nor would it be the last. By the spring of 1943, nearly 200 Liberty ships had suffered severe structural fractures, and several dozen had split entirely in two, some at sea, taking their crews with them. The press avoided the subject under wartime censorship, but in naval and engineering circles the panic was spreading. The vessels that Henry Kaiser's shipyards had once built faster than anyone believed possible symbols of industrial triumph were now cracking open like eggs. In Washington, Vice Admiral Howard Vickery of the U.S. Maritime Commission called an emergency meeting. Engineers from the Bureau of Ships, representatives from Kaiser's yards in Richmond, and civilian, metallurgists from the University of California, Berkeley, gathered in a closed session. The question was painfully simple. Why were America's miracle ships falling apart? The early theories bordered on superstition. Some blamed sloppy welding by untrained workers. Others pointed to poor steel from overworked mills. A few muttered about sabotage. But within months, a more disturbing pattern emerged, one no one had expected. The fractures always began the same way. A small, jagged crack along a welded seam near a hatch corner or deck joint, spreading silently until catastrophic failure. And at the center of this industrial crisis stood an unlikely figure, a quiet, bespectacled civilian metallurgist named Constance Tipper. In the winter of 1943, Tipper had been working in Cambridge, England, studying the brittleness of low-carbon steels under extreme cold. When the Liberty ships began snapping in the North Atlantic, British and American officials sent her samples of fractured hulls to examine. What she found shocked the maritime establishment. The steel itself was sound chemically and structurally normal by every pre-war standard. The problem wasn't the metal, it was how it had been joined. Traditional shipbuilding for centuries had relied on riveting, overlapping plates fastened by heated metal rivets hammered into place. Riveted joints could bend, flex, and distribute stress gradually. Welding, by contrast, fused plates edge to edge, creating continuous seams of hardened metal. It was faster, lighter, and theoretically stronger, but in cold temperatures, those rigid welded seams became brittle. A tiny crack, often invisible, could travel through the steel at the speed of sound, splitting the ship like glass. The Liberty ships had been mass-produced under Henry Kaiser's revolutionary welding program, built by men and women who had learned the craft in weeks rather than years. Their welds looked perfect under peacetime conditions. But in the Arctic, where temperatures dropped below -10 degrees Fahrenheit, the metal lost its ductility. Each ship became a potential time bomb. Tipper's analysis, later confirmed by American metallurgists, revealed a chilling fact. The steel itself underwent a transition known as ductile to brittle fracture around freezing point. In other words, the metal that could bend and deform at room temperature would suddenly shatter under cold stress. The continuous welded seams provided no natural stopping points for cracks, no rivet holes to arrest their spread. Once a fracture began, it ran unchecked until the hull split in two. The Maritime Commission, desperate for a fix, launched a secret investigation code-named Project Liberty Bell. Over 50 ships were inspected across multiple shipyards. Cracks appeared everywhere around hatches, in deck corners, near bulkheads. Some were mere inches long, others stretched across the hull. Shipyard workers called them Christmas trees because of their branching shapes. Yet, amid the chaos, one small shipyard in San Pedro, California, reported something strange. Their Liberty ships weren't cracking. Not one. The reason traced back to a civilian welder named Robert G. Dexter. Dexter was not a naval architect or metallurgist. He was a pipe welder from the oil industry, an outsider who had joined the emergency shipbuilding program in 1941. Unlike most welders, Dexter had experience joining thick cylindrical pipes for oil refineries, where thermal expansion and contraction could tear ordinary welds apart. He'd learned to lay down his seams in a spiral or weave pattern, alternating directions and overlapping passes to distribute stress. When assigned to the hull section team at California Shipbuilding Corporation, Dexter noticed that standard Liberty ship welding patterns followed rigid, straight seams, aligned perfectly with the steel plate's edges. To him, it looked wrong. Those continuous, straight seams would concentrate stress, just as oil pipelines did when improperly joined. So Dexter changed it, quietly. He began instructing his team to weld hull plates with alternating, slightly offset patterns, breaking up the continuous lines of tension that ran across the hull. Instead of long, straight seams, his pattern resembled a series of staggered stitches. Supervisors initially called it absurd, even ugly. But his ships, the SS John Mercer, the SS Ada M. Wills, and others returned from North Atlantic runs intact, with no visible cracking. When Navy inspectors arrived in early 1944 to examine Liberty ships with perfect records, Dexter's unconventional welds drew immediate attention. At first, engineers dismissed them as sloppy work. Then, Tipper's findings from Cambridge arrived. Her metallurgical analysis explained why Dexter's pattern worked. By interrupting the straight-line continuity of welded seams, his overlapping pattern absorbed and dispersed fracture energy. The tiny irregularities acted as crack arresters. The absurd-looking pattern was, in fact, saving ships. Before the war, no engineer would have accepted such an approach. Naval construction manuals demanded symmetry, precision, and perfect alignment. Every weld had to run true along the line of stress, not against it. But the war had already upended centuries of tradition. Civilian ingenuity, Kaiser's prefabrication, Chrysler's assembly line tanks, Ford's Willow Run bombers, was rewriting the laws of industrial warfare. By 1944, the U.S. Maritime Commission quietly issued new welding guidelines incorporating elements of Dexter's offset pattern. They required crack arrestor seams, stress relief cuts, and staggered joints along high-strain areas. The policy was never publicized. Wartime secrecy buried the details, but shipyard production data revealed the result. By the end of 1944, Liberty ship fractures dropped by nearly 70%. The hulls still cracked occasionally, but they no longer tore themselves apart. And in post-war metallurgical studies, one line from the Cambridge report stood out. The salvation of the Liberty hull lies not in the perfection of the weld, but in its imperfection. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. That single insight born from a civilian's absurd deviation transformed shipbuilding practice. In later decades, fracture mechanics would become a formal field of study, pioneered by researchers like George Irwin at the Naval Research Laboratory. But the principle began not in theory, but in the practical instinct of a wartime welder who simply refused to follow the line. The Liberty ship crisis remains one of the most ironic chapters in wartime engineering. The very innovation that made mass production possible welding nearly destroyed the fleet it had created. Yet it was saved by another innovation, equally unorthodox, equally human. In the spring of 1944, at a nondescript facility on the Potomac River near Washington, D.C., a team of engineers gathered around a long steel plate suspended between hydraulic clamps. The Naval Research Laboratory had been ordered to replicate the Liberty ship fractures under controlled conditions. Their goal was to find the precise combination of stress, temperature, and weld geometry that could split an entire hull. The test piece, 30 feet long and 1 inch thick, was chilled to 20 degrees Fahrenheit. A sharp notch had been machined into the edge to simulate a flaw in the weld. When the hydraulic press applied force, the crack raced across the plate in less than a second. The steel didn't bend. It snapped, clean through, with a gunshot-like crack. The test confirmed Constance Tipper's findings from Cambridge. The transition from ductile to brittle behavior occurred just above freezing, and the continuous welded seams offered no resistance. The very efficiency that made Liberty ships possible, the seamless, all-welded hull, had also eliminated their margin for forgiveness. In engineering terms, the Liberty ship crisis revealed a new and frightening phenomenon: low-temperature, brittle fracture. But in human terms, it represented a collision between two philosophies, one ancient, one industrial. The old school of shipbuilding believed in craftsmanship: rivets, overlapping plates, incremental strength built layer by layer. The new order, born of wartime necessity, believed in speed, uniformity, and repetition. The two systems met at the seam line, and the seam line broke. At the Richmond Yard in California, the atmosphere had changed. Where once the assembly lines rang with optimism, now every new launch carried a shadow of doubt. Inspectors with flashlights walked the decks, searching for hairline cracks. Women welders, many of whom had left domestic jobs to build ships for the war, watched as their work was tested to destruction. Yet amid the anxiety, quiet experimentation continued. At the behest of the Maritime Commission, a small team led by civilian welding engineer Edward N. Bain from the U.S. Steel Research Laboratory began testing alternative welding sequences. Bain, a metallurgist by training, was fascinated by Dexter's pattern reports from San Pedro. He requested access to sample plates welded according to Dexter's offset method. The results were astonishing. When struck or chilled, plates welded with continuous straight seams fractured completely across their width. Plates welded with Dexter's alternating or weave pattern developed cracks that started but stopped within inches. The irregularities in the seam redirected stress, dissipating energy in small zigzags rather than allowing a single catastrophic break. Bain's formal report, filed in July 1944, used language so understated it almost concealed its significance. The distribution of stress through non-linear weld geometry appears to introduce discontinuities beneficial to crack arrest. In simpler terms, the ugly welds didn't fail. That conclusion, though scientifically sound, created an institutional dilemma. The Bureau of Ships had spent 3 years standardizing welding manuals that demanded straight, even seams. Every inspector had been trained to reject anything that deviated from the official line. To endorse a pattern that looked wrong would mean admitting that visual perfection could equal structural weakness. The Navy's Chief of Ship Construction, Rear Admiral Edward L. Cochrane, hesitated. Officially, no such pattern could be adopted without testing under service conditions. Unofficially, he authorized a quiet trial. 3 Liberty ships nearing completion, SS George S. Boutwell, SS Mary Livermore, and SS William J. Worth, were each assigned modified welding procedures incorporating offset seams and crack arrestor joints. These seams alternated direction every few feet, creating a subtle zigzag visible only under close inspection. The welders who implemented them, many trained under Dexter's informal guidance, nicknamed the new layout the basket stitch. All 3 ships launched from California yards in the late summer of 1944. Each was routed into the North Atlantic convoy system, the ultimate proving ground. Through the winter storms of 1944 to 45, as temperatures dropped below zero and ice sheathed the decks, inspectors waited for the inevitable telegrams reporting fractures. None came. Meanwhile, conventional Liberty ships continued to suffer minor cracking, though catastrophic failures had lessened since the new steel specifications and crack arrest features were introduced fleet-wide. By March 1945, data from the Maritime Commission revealed a stark contrast. Ships built with the modified weld pattern had 0 recorded hull failures. Traditional welded hulls still produced dozens of incidents each month. The absurd welding pattern had become the quiet standard. The deeper irony lay not only in the technical success, but in what it revealed about wartime psychology. The Liberty ship program had always embodied America's industrial faith that speed and standardization could outproduce any enemy. Yet when those ships began breaking in half, the response was not to slow down, but to look sideways to the individuals who thought differently. Dexter, the civilian welder whose pattern sparked the change, never sought recognition. His name appeared in no official reports. Like thousands of workers in Kaiser's shipyards, he returned to civilian life after the war, his contribution buried beneath layers of bureaucracy and classified memoranda. Constance Tipper fared differently. Her studies of brittle fracture earned her recognition as one of the pioneers of fracture mechanics. After the war, her Tipper test, a simple bend test for assessing steel toughness, became standard practice in shipbuilding and bridge design worldwide. Yet, even she acknowledged, years later, that the real innovation had come not from theory, but from instinct. In an interview with the Engineer magazine in 1952, she reflected, "We discovered scientifically what welders already knew intuitively, that steel, like people, must be allowed a little imperfection to survive the cold." As the Liberty ships sailed into history, their patched and modified hulls became the backbone of post-war trade. Many were sold to private shipping companies, converted to freighters, and sailed for decades under foreign flags. Inspectors in the 1950s noted that those built with the basket stitch pattern exhibited less fatigue damage than their straight-seamed predecessors. Historians now view the Liberty ship crisis as a turning point, the moment when metallurgy, engineering, and psychology collided. It forced the birth of fracture mechanics, reshaped naval architecture, and humbled the myth of industrial infallibility. And it all began with one man's refusal to weld a straight line. When the war ended in August 1945, the shipyards fell silent almost overnight. Cranes stood idle. Sparks no longer danced across the hulls. The thousands of men and women who had welded America's bridge of ships returned to quiet lives, teachers, farmers, clerks, mothers. The nation had moved on, but the Liberty ships remained, scattered across the world's oceans like steel fossils of a fevered age. In their holds now rested cargoes of grain, machinery, and hope instead of tanks and ammunition. Yet beneath every deck, the seams told a story, the story of trial, failure, and stubborn adaptation. In Washington, committees convened to analyze what had gone wrong and why. The official reports were sober, almost apologetic. The U.S. Maritime Commission concluded that brittle fracture under low temperatures was the primary cause, aggravated by design rigidity and inadequate notch toughness in the steel. It was an engineering statement, clean and bloodless. It did not mention the panic, the midnight telegrams, or the shame of watching ships sink from their own making. And it certainly did not mention the welder from San Pedro, whose unapproved welds had outperformed the manual. But inside the Bureau of Ships, lessons had been learned that would change the entire field of naval construction. New standards required crack arresters, rounded corners, and weld sequence variations. Welders were trained not only to follow blueprints but to understand the flow of stress through the steel. The once absurd offset seams became part of official doctrine, adopted under sterile new terms like staggered stress distribution geometry. The spirit of Dexter's pattern lived on, but his name did not. The Liberty ships themselves continued to serve. By the 1,950 seconds, more than 2,000 were still in operation, many refitted for peacetime trade. Mariners came to trust them again, though the myth of their invincibility had been replaced by a quieter respect. One old captain, interviewed in 1957, said it best: "You learned to listen to a Liberty ship. The steel had a voice. It creaked, it groaned, but it told you it was alive. The ones that didn't talk were the ones that scared you." In those words lay an echo of the entire saga. The idea that perfection without flexibility leads to silence, and then to fracture. In the academic world, a new discipline was taking shape. At Cambridge, Constance Tipper's students expanded her research into what would become fracture mechanics, later formalized by scientists like A. Griffith and George Irwin. Their studies found their way into every field that dealt with stress and failure: airplanes, bridges, oil rigs, even spacecraft. When NASA engineers designed the Apollo Command Module in the 1960 seconds, they referenced early ship fracture data from the Liberty ship crisis. The hard-earned lesson of 1943 that a single overlooked flaw could doom an entire structure became a guiding principle in the space age. Each rivet and weld in those later machines carried the ghost of a broken hull in the North Atlantic. And what of Dexter, the welder who had defied the manuals? His name surfaces only in a handful of oral histories collected by the Kaiser Shipyard's Heritage Foundation. A few former foremen recalled him vaguely. A quiet man in his 30s, chain-smoking between shifts, always tinkering with new weld angles. When asked why he worked the way he did, one remembered him saying simply, "Straight lines break easier." No medals were awarded, no newspaper articles bore his name. Yet his insight, born not from schooling but from lived intuition, saved hundreds of lives and billions in cargo. It was a reminder that innovation often hides in plain sight among those who don't have the authority to speak, but the courage to question. By the 1980 seconds, only a handful of Liberty ships remained afloat. Most had been scrapped, their steel recycled into cars and skyscrapers. One survivor, the SS Jeremiah O'Brien, restored in San Francisco, became a living museum. Visitors walking her decks can still trace the uneven seams beneath the paint, tiny irregularities in the welds that tell of a time when imperfection became salvation. If you look closely enough, some of those seams curve slightly, defying the ruler-straight uniformity of the original blueprints. They are, quite possibly, the last visible remnants of Dexter's absurd pattern. History often remembers generals, admirals, and presidents. It writes their names in marble and bronze. But the story of the Liberty ships is a quieter kind of legacy, one written in steel, in mistakes, and in the humility of correction. The ships that once broke in half taught engineers to design for the unthinkable. They proved that failure, when studied and embraced, becomes the seed of resilience. And above all, they whispered an uncomfortable truth that resonates far beyond shipyards. Perfection is brittle. Imperfection endures. When the last Liberty ships were finally retired, the world they had helped forge was already unrecognizable. The war that had demanded total industrial mobilization had also rewritten the very language of engineering. Yet, like an echo buried in the steel of every vessel and bridge that followed, the lessons from those fractured hulls continued to resonate. The Liberty ship crisis had forced a reckoning. Technology could not be divorced from humility. That revelation, though born of panic, became the seed of a global transformation that would ripple through the second half of the 20th century. In the years immediately after 1945, engineers across the United States, Britain, and Japan pored over data from the Liberty program. Constance Tipper's British team collaborated with American metallurgists at the Bureau of Ships and the U.S. Steel Research Laboratory, they compared field failures with laboratory fracture tests, building a library of crack propagation data unlike anything compiled before. By 1948, George Irwin, at the U.S. Naval Research Laboratory, began formalizing these findings into a new scientific framework he called fracture mechanics, a method of predicting how and when cracks would initiate and grow. For the first time, engineers could quantify toughness, not just strength. It was a paradigm shift. Before the Liberty disasters, steel had been judged mainly by tensile strength, the ability to withstand force before breaking. But fracture mechanics introduced the idea that a structure could fail long before reaching its theoretical limit if microscopic flaws spread unchecked. Designs would never again rely solely on bigger and thicker. They now had to account for the invisible. Within a decade, this theory became the backbone of aerospace design. When Boeing engineers developed the 707 jetliner in the 1950 seconds, they used Irwin's equations to calculate stress around rivet holes and cabin windows. The concept of fail-safe design, where cracks could start but not spread, was born directly from the Liberty ship experience. Every time a passenger plane flies safely through turbulence, it carries a trace of that wartime revelation. As the Cold War dawned, steel became the language of global power. Supercarriers, submarines, and oil tankers grew larger with every decade. The United States and the Soviet Union raced not just to build weapons, but to master materials science. Ironically, the Liberty ship, once derided for its crude construction, became the unsung prototype for the industrial gigantism that followed. The modular building techniques perfected in the 1,940 seconds inspired everything from prefabricated housing to massive, container ships, and the safety lessons embedded in their failures guided each new generation of naval architects. In 1958, the USS Nautilus, the world's first nuclear submarine, was launched using steels derived from the same fracture-tested alloys developed in the Liberty era. The submarine's designers used data from brittle fracture tests conducted on old ship hulls. The ability to operate deep under polar ice, where temperatures could plunge to 40 degrees Celsius, was made possible by that data. Even in the Soviet Union, far from the San Pedro shipyards where Dexter once welded, researchers quietly studied translated reports on Liberty ship cracking. A 1957 Soviet metallurgy journal quoted Irwin and Tipper, noting that crack arrest by geometry variation was a potential safeguard for Arctic hulls. Though they never mentioned Dexter, they replicated his offset weld method almost exactly on ice-class tankers built in Leningrad. Thus, the absurd pattern crossed ideological lines, uniting enemy engineers under the same principle: imperfection saves. The 1,960 seconds were an era of breathtaking ambition. Architects and engineers began to treat steel as limitless, stretching it across canyons, stacking it toward the clouds. But even in the optimism of the space race, the ghosts of the Liberty ships lingered. In 1967, the Silver Bridge over the Ohio River collapsed, killing 46 people. Investigators found that a single, undetected crack in an eye-bar had propagated catastrophically, a textbook case of brittle fracture. The lessons of the 1,940 seconds returned with vengeance. The field of structural forensics expanded overnight, demanding routine fracture toughness testing for bridges and high-rise structures. Engineers who had once served in wartime shipyards now became professors, teaching new generations to respect the hidden flaw. Many cited the Liberty ships as the first modern disaster of materials science. Their mantra, "A structure is only as perfect as its ability to forgive imperfection." From that principle flowed the redundancy designs of the World Trade Center in 1973, the fail-safe wiring of nuclear power plants, and even the flexible steel skeletons of earthquake-resistant skyscrapers in Japan. The Liberty ships had died so that millions of future structures might bend, not break. By the 1,970 seconds, only a handful of Liberty ships still sailed, mostly as bulk carriers or training vessels. Their hulls, now obsolete, were quietly sold for scrap, but even in dismantling, they gave again. Steel recovered from Liberty ships was unusually pure. Wartime production had avoided impurities like sulfur and phosphorus that promote brittleness. That recycled steel found its way into new bridges, highways, and buildings around the world. In one poetic twist, portions of old Liberty ship steel were melted down for use in the San Francisco-Oakland Bay Bridge retrofit of the 1,990 seconds, returning to the same coast where many had been born. The atoms themselves had come full circle from ship to bridge, from war to peace. As the 20th century gave way to the digital age, the spirit of Dexter's defiance re-emerged in an unexpected place: software engineering. By the 1,990 seconds, computer scientists began speaking of fault tolerance in code, systems designed to keep working even when parts fail. The language was eerily familiar to any materials scientist. Where Liberty ships had taught the importance of crack arrest, programmers now learned the value of graceful degradation. When NASA built the Space Shuttle, engineers relied on fracture mechanics equations derived from those 1,940 seconds papers. When Apple designed the first iPhone chassis, Its finite element simulations used the same stress distribution mathematics once applied to ship hulls. And when modern AI researchers talk about robustness systems that continue learning despite noisy data, they echo the same insight. Strength isn't perfection, it's adaptability. Absurd weld had become a metaphor for the entire modern era. Yet something curious happened as technology advanced. The very efficiency that had caused the Liberty ship crisis, the faith in uniformity, in systems that never returned under new guises. Automated design tools promised flawless blueprints. AI-driven factories produced seamless precision parts. The human touch, once blamed for inconsistency, was again being eliminated. In 2005, a small engineering firm in Glasgow conducted a study comparing robotic and manual welding in ship hulls. Their conclusion startled the industry. Robotic welds, though perfectly even, were less resistant to crack initiation than slightly irregular manual welds. The explanation? Micro-variations in manual seams disrupted stress waves exactly as Dexter's basket stitch pattern had done 60 years earlier, one engineer quipped in his report. We may have to teach the robots how to make mistakes. It was the circle closing once more, the machine rediscovering the wisdom of the human hand. Today, the SS Jeremiah O'Brien in San Francisco and the SS John W. Brown in Baltimore stand as floating memorials to that wartime fleet. Visitors who step aboard rarely notice the weld seams beneath the paint, but to an engineer, they speak volumes. Each curved line, each uneven bead of metal, is a frozen moment of innovation, a conversation between instinct and instruction. Restorers still point out sections of the hull where non-standard welds were preserved, believing they were part of the experimental crack arrest trials of 1944. When the O'Brien steamed back to Normandy in 1994 for the 50th anniversary of D-Day, her engines throbbed steadily across the Atlantic. The welds held, exactly as Dexter had once imagined they would. Standing on her deck, surrounded by veterans who had once feared the very sea that split their ships, historians could almost feel the ghost of that forgotten welder smiling quietly in the smoke. The Liberty ship saga is now taught not only in engineering schools but in management and design ethics courses. The reason is simple. It's not merely a story about metal, it's about mindset. During World War II, production schedules ruled all. Mistakes were punished, deviation discouraged, innovation stifled by urgency. The collapse of those ships revealed what every complex system eventually learns, that efficiency without curiosity is fragility in disguise. Dexter's absurd weld became a parable of creative dissent, the courage to be wrong long enough to find what's right. Modern organizations, from tech companies to healthcare systems, now invoke psychological safety as a core value, the freedom to question authority without fear. In a sense, every brainstorming session where an unconventional idea survives owes something to a welder who refused to make his seams straight. If there is a single phrase that captures the legacy of the Liberty ship crisis, it might be this: redundancy saves lives. That idea has evolved into countless safety standards. Aircraft must sustain flight with one engine out. Data centers maintain backups across continents. Financial systems run stress tests to ensure partial collapse doesn't mean total ruin. All of these are conceptual descendants of a cracked hull in the Arctic Sea. Even climate change engineering designing wind turbines, sea walls, and renewable grids relies on those same mathematical principles of resilience. The brittle ship that once broke in half became the teacher for a planet learning to survive under pressure. In 2015, historians from the Kaiser Shipyard's Heritage Foundation uncovered payroll records from the Richmond Yard. Among thousands of names was a line item: Dexter A. Field Welder, Dept. 34. No further information existed, no address, no commendation. But they found something else. A maintenance report noting that Field's crew exhibits superior crack resistance results using alternating seam technique. It was the first written acknowledgement, however small, that someone had noticed. In 2018, a group of engineering students at Cal Poly built a small test model of a Liberty ship hull using Dexter's pattern. They chilled it to 10 degrees Celsius and applied stress until failure. The model bent, groaned, and held. On the lab wall behind it, someone had pinned a sign, "Straight lines break easier." That simple phrase has since become an unofficial motto for the program's materials science department. Standing today in a shipyard, whether in Busan, Shanghai, or Newport News, one can trace the lineage of those wartime lessons in every hull and beam. Computer-controlled plasma cutters follow patterns optimized for stress distribution. Welders still stagger their seams, though the practice now goes by the sterile label multi-pass offset sequencing. Few know the origin, fewer still know the name Dexter Field. But every ship that leaves the dry dock carries a whisper of his defiance. Every time steel survives the cold, the absurd becomes rational once again. In a broader sense, that is the enduring legacy of the Liberty ships, not the steel, not the statistics, but the idea that progress depends on those willing to look foolish before they look brilliant. If you could step back and look at history itself as a vast sheet of steel, you might see that it, too, bears Weld's connections between eras, between triumph and mistake. Some seams are straight, efficient, and invisible. Others wander slightly, curving where a hand once trembled or a mind once dared. And maybe that's why history endures, because its strength lies not in being perfect, but in being patched, repaired, and reimagined by those who refuse to give up when things crack. From the Liberty ships that split in two to the spacecraft that now glide beyond the atmosphere, the lineage is unbroken. Every advance, every safeguard, every impossible design owes something to that cold Atlantic night when a hull failed, and to a civilian welder who refused to accept that it had to. The world learned to weld differently because one man welded differently, and though the name Dexter Field may never appear in textbooks, his pattern endures everywhere that steel meets sea, sky, or silence. In that sense, the absurd has become immortal. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.